Let me introduce TAILCHECK. I'm Amogha, joint work with Raveendra, Soori, Professors Michael Ferdman and Dongyoon Lee. So we are targeting the heap buffer overflow, and we are using two key ideas, which is page protection and tag pointers. Page protection has been around for a very long time, used in buffer overflows, but to detect buffer overflows. We'll see how we can use an old idea with a new idea like tagging pointers. All right, why do we care about heap overflow? C and C++ are widely used, very efficient, but you still have no memory safety. So you have all sorts of memory issues, be temporal, spatial. Heap overflow is in fact dangerous because it's one of the most, one with a high security implications. So it was in fact, out-of-bound write was said to be the topmost dangerous software weakness for 22 CWE, same for 21. Out-of-bound write has been a top dangerous weakness for several years in the top few rankings. So security implications, we can have privilege escalation. Here we are seeing heap-based buffer overflow in sudo. This was a write overflow. And this can also, read overflows can also cause issues. For example, information leakage, like in the classic heartbleed bug in the SSL. There have been prior solutions to tackle heap overflow. Let's look at a very old solution such as electric fence or page heap, where they use guard pages. Guard pages are pages that are just aligned to the end of allocations. So you see when you ask for an allocation from the allocator, it'll ask for a page, even though it's a small allocation, and it'll allocate the object at the end of the page. And starting from the end of the page, the next page is protected. So any out of bounds, or if you go over the object's size limits, it'll hit the guard page, and that'll trigger a segmentation fault. But here you see the good part is you don't have to look up any metadata. Just any normal program flow would result in errors if there's an overflow. But however, it requires high memory overhead, and there's a lot of system calls to protect the buffer. So there's a cost of performance as well. There can be explicit bounds checks like softbound. It uses a shadow memory region, but it has metadata lookup and comparison costs, which are again not viable. Pointer tagging is a more recent approach. It has quick metadata lookup because the metadata is stored in the higher order bits of the pointer. But some solutions that have been proposed previously requires larger tags, which requires the shrinking of address spaces. So let's look at TAILCHECK now. How can we protect this blue object right there? So we use page protection by aligning a tail object, which is a shadow object. We don't care about what is in that object. It's just allocated for an original object as a tail object, and its end is aligned to a guard page. And how can this provide protection? Well, if we can duplicate the memory dereference of any original object on the tail object, then any overflows of the original object will be resulting in hitting the guard page. But how can we duplicate the memory access? How do we know where the tail object is? Well, that's where we use tag pointers. So we store where the tail object is in the tag bits of the pointer, so on the higher bits of the pointer. So any memory dereference we have in the program point, we just have to extract the tag bits, add it to the pointer, and then we directly reach the tail object. Let's see how, if it's in the bounds, we'll hit the tail object, but if it's out of bounds, we hit the guard page. So out of bound access will directly result in page faults which can be caught. We have seen an introduction to TAILCHECK. Let's dig a bit deeper and see how we allocate these objects, how we manage the tail pointers, and how we duplicate the memory dereferences. We'll also see the evaluation of TAILCHECK. TAILCHECK design, we have two major components. First, we need to align the objects as per the requirements of tail objects. For example, we're talking about setting up guard pages here, setting up the tail object, and also finding out the distance to the tail object and tagging the pointer bit. So allocator does two important things. One is to set up the guard pages. Second, initialize the pointer tags. Next part is the memory dereference duplication, for which we use compiler instrumentation. So we need to duplicate the memory dereference, also make sure that the tag bits are not passed on to external uninstrumented libraries. So all our instrumentation happens within a boundary of the program, and if we pass that boundary, the program doesn't understand what the tag bits are, and that can result in some issues. So we have to make sure that any pointer that crosses the boundary of the instrumentation is cleaned. Now, memory allocator, we have seen briefly how the tail object exists, but how do we allocate it? How can we make this fast? So the key idea is to share the tail object among many different objects. So here we see a group of blocks, and we use memalloc based allocator. So memalloc will make a free list for every object size. So there are free blocks, and we allocate a block out of one of the blocks, and the last block of this particular group of blocks is the tail object. And this entire group of objects can be then, whose end can be aligned to a guard page. So at every point, if we allocate a block, that can share the same tail object. So if we load or store on the original objects, any one of the previous original objects, the same memory access is performed on the tail object. So we see that we can represent up to a certain distance in the tail tag. So since the higher order of the pointer carries the distance to the tail object, we are limited by what the size of the tag is, and that is 16 bits in our case, which can represent up to 64 KB. And tail tag is then, we have to calculate what is the distance from within the allocation to the tail tag, and then we tag those bits onto the pointer. So when the when the allocator returns back to the program, it'll have the tag bits in the pointer itself. And since this is implemented as a compiler pass, which we'll talk about later, we can then extract this tail tag for duplicate memory access. Now we talked about 16-bit tail tags. What about tail objects which are higher than 64 KB? Well, in that case, we fall back to the older method of aligning the guard pages directly to the memory allocations. So here we see that for larger objects, they are their own tail objects. And the tag here is 0, because we don't have to go anywhere for getting protection from buffer overflows. Any out-of-bounds access on the large objects will result in hitting the guard page, and thereby providing implicit protection without requiring any sort of calculation here. But since from a program point of view, we don't know if the tail tag is 0 or non-zero. So we have to instrument the same way for both large objects and single objects. So this sort of a uniform solution here for two different kinds of protection. Now talking about instrumentation, so we see that how from the allocator we can get a tag pointer, but how can we then duplicate the memory dereference? Well then, we simply have to extract the tail bits and the pointer bits. The pointer bits are in the lower order bits, which address the object, and the tag bits are in the higher order bits. So we can just use the operations of and right shift to get the pointer and the tail tag. We then add an additional dereference, here in this case load p plus d, so where p is the pointer to the object and d is the distance to the tail object. So thereby we replicate the memory dereference on the tail object. We use LLVM link time optimization passes as our means of providing instrumentation. So there are several passes here. Firstly, we have to duplicate the memory dereference. That simply goes over all the list of dereferences, and then we can perform those operations that I just mentioned. And then we also have to do call site masking, where at any call site, if the pointer is going out of the boundaries of the particular program, we have to remove the tags. And there are also some optimizations. For example, safe alloc is delta pointers optimization for removing statically known safe accesses, so we don't have to check them. Then we also hoist tail pointer calculation out of the loops. So we saw how we have to extract the delta or the tag bits from the pointer. Well, we don't have to do it inside a loop. We can extract that out of the loop and just have 2 pointers. One pointer that points to the object and another pointer that points to the tail object. So we can just perform the same pointer arithmetic on the 2 objects, thinking about them as 2 different objects. And then we save a lot of CPU cycles there by not having to extract the tag, because the tag is constant throughout the program. Now that we have seen how we have designed and implemented TailCheck, let's look at the evaluation. For evaluating TailCheck, we used server applications and we used SPEC benchmark suite. Server applications, we used 4 server applications. 2 of them were web servers and 2 key value stores. For Apache and nginx, we used 256 requests per second, varying the load size. And for memached and redis, we used 50% get-set ratio, again varying the value sizes of what is inside. And for SPEC CPU benchmarks, we used both 2006 and 2017. 2006 because it was, a lot of works had used 2006 to evaluate it, so we still wanted to evaluate with 2006. And 17 because it's latest and greatest. Security evaluation, we've seen how buffer overflows are caught as segmentation faults. 2006 SPEC didn't have any heap buffer overflows, but 2017 GCC had an illegal read that we detected. This was a 4-byte read out of an allocated area, and this can be solved by checking for out of bounds within the program. This was detected in SPEC CPU2017 benchmark. Let's look at the server application performance. We said four servers, but here we have an extra for nginx because we could also disable the pool allocation. For some servers, it is by default, but some servers we can turn them off. With nginx, we could turn them off, and so here we present the performance of all of those server benchmarks. We see less than 4% tail overhead, which means that when we query or when we dump the requests on the server, we measure it for a certain period of time, giving it a constant rate of request per second. So we measure the 99th percentile, and for both address sanitizer and for our own TailCheck, we see that our performance is 3x better compared to address sanitizer. Looking at SPEC performance, for SPEC's CPU 2006, we compared the performance of TailCheck with Delta Pointer. We see that we perform better than Delta Pointers in SPEC 2006. This is mainly because Delta Pointers have a distance to the end of the object, and they keep updating their tag for every pointer arithmetic. So which can turn out costly in certain type of programs, which explains the performance difference between TailCheck and Delta Pointer. For SPEC 2017, TailCheck overhead is 33%. We also provide the measurement of memory overhead for our solution, details of which are in the paper. To conclude, TailCheck offers page protection-based heap memory safety. We use a combination of allocator and compiler instrumentation for managing tag pointers. Here we see that duplicate memory dereference implicitly acts as an out-of-bounds check. We don't have to check for if a pointer access is out of bounds based on some metadata here. We saw that optimizations improve the TailCheck performance by 20%. We saw in SPEC 2017 where we have different levels of optimizations that we provide on TailCheck. TailCheck is fast and it can be run in production. We saw how there's a 4% and 3% average and tail latencies for the server. And it also performs well on SPEC's benchmark suits, SPEC 2006 and 2017 with overhead of just about 30%. That's it, thank you.